This is the second part of my lecture on limits. In the first part, we talked about what a limit is and how it can exist independent of the function value. So we said the limit as x approaches a of f of x. We say that equals L if we can get as close to L as we want just by taking x values sufficiently close to a. And then we said that f of a, the function value at a, has nothing to do with L. Right? They might be the same, they might not. We saw plenty of examples of that. In this lecture, what I want to look at is how this limit might fail to exist. So the first thing I want to go over is this idea of one-sided limits that I talked about a bit in the first lecture. So we say the limit as x approaches a from the left, that's what that means, of f of x. And you can think of this as, if you think of the x and y axes, right, that, as you go farther left, you're negative, and if you go farther right on the x-axis, you're positive. So if we're looking at, I'll just kind of draw on a quick function here, so if this is a, and we're approaching this point from the left, that's how we denote. All right, so that's the left-hand limit, and then I'm just going to put it in. I'll put right here. So we take the limit as x approaches a from the right. So that would be coming at it this way. I want to point out that this just says you're coming from the left, and this just says you're coming from the right. It doesn't mean that our x values are negative or positive. It's just kind of indicating what direction we're coming at it from. So this is the limit as x approaches a from the right of the same function. So now we have a limit. In other words, this could converge to a particular y value. This could also converge to a particular y value. But if those are the same, we say if the left-hand limit and the right-hand limit are the same, then the limit exists. All right, so we could actually say a little bit more. So let's suppose that limit as x approaches a from the left of f of x equals L, and limit as x approaches a from the right equals L, then this implies that the limit as x approaches a of f of x exists, and it equals that point that these are converging to. All right. Okay, so one significance of this is that this shows us, since this follows from that, if this fails, then this doesn't work. All right. So let me rewrite that then. Let me just put this in a different color here. So we're going to say if, it actually follows from the converse, but if the limit as x approaches a from the left does not equal the limit as x approaches a from the right. In other words, this could be, let's call it L1, and this could be a different, so it could converge to a particular y value, we'll call it L1, maybe this one converges to L2, right? And I'll draw a picture of what this might look like, but the point is they're not converging at the same point. They're kind of missing somehow, right? And so if they're going to different points from the left and the right, then we don't have a limit because they need to kind of converge to the same point. So if this happens, then the limit as x approaches a of f of x, I'm just going to use my shorthand, does not exist. Okay, so let's take a look at an example of how that might fail. All right, I'm going to draw it graphically. Okay, so let's say we have some curve coming in this way, and there's the function value. We'll call this a, and then we have the same function. Maybe it's coming in this way, and it's open here. Right? We can't have both of them filled in because then I would have two y values associated with one x value, and we wouldn't have a function. And we want this to be a function. We're going to call this f of x. It's both of these curves. All right. So here's a. So I'm going to call this y value right here L1, and this y value right here I'm going to call L2. So the limit as x approaches a from the left, so as we get closer and closer to a from the left, we can see that our function value up here is approaching that y value. We'll call it L1. All right. So this over here. So from the left, the limit is L1 because we can get closer and closer to L1 by taking a values from the left. Sorry, taking x values from the left of a. So basically, values of x that are smaller than a, be getting closer and closer and closer to a, will get us closer and closer to L1. And then likewise, the limit as x approaches a from the right of f of x equals L2, because as we approach from the right, these y values are going toward that y value right there. So in this case, since these are not equal, then the limit as x approaches a of f of x does not exist. All right. So what's just like we said before that, I was saying that the function value has nothing to do with the limit existing. That's also true for one-sided limits. All right. So for the fact that the function value is here has nothing to do with the fact that this limit is L1. We can see that from over here, right? Because in this case, the function value isn't there. It's up here, but the limit, the right-hand limit, still exists. I mean, so, one example that could exemplify that, we could have something that looks very similar, except we have a hole here, and we're coming down like this. We have a hole here, we'll call that L1 again, we'll call this L2 again. Let's say the function value is in between. So if this is A, then here's f of a right here. All of this still applies to this situation. The limit, the left-sided limit is still L1. The right-sided limit is still L2. Therefore, the limit still does not exist because we have this type of a thing going on. Again, just to reemphasize, the function value has nothing to do with the existence of the limit. In fact, you might not have a function value at all, right? We could just have two open holes here, and then this would still apply. So this is an important thing to understand, this idea of one-sided limits. So one way to show that a limit exists is to show that the one-sided limits exist and that they equal the same thing. Then this follows. The limit exists, and it's whatever those one-sided limits are. Likewise, if we can show that the one-sided limits either don't exist or they exist and they're not equal, and we'll see an example a little bit later about how they might not exist, then our limit doesn't exist. So that's one way. The left and right hand limits don't agree. Let's look at another one. All right. So another way that the function can fail, or the limit can fail to exist. So let's look at this example of f of x equals 1 over x. All right, and I'm interested in the limit as x approaches 0 of 1 over x. So the graph, you may recall, is going to look something like this. All right. So as we get closer and closer to 0, these function values just get larger and larger and larger because we're dividing by smaller and smaller numbers here, right? If you divide by 0.1, you get 10. If you divide by 0.01, you get 100. If you divide by 0.001, you get 1,000. So this thing is just blowing up here as you get closer to 0 from the right. And then from the left, this thing is just kind of diving down to negative infinity, all right? We can look at this also in terms of a table, right? So let's go... I want to look at this one. So there's the graph that I just drew, and let's look at the table. So if we go to, we want to be right at 0 on our table. Yeah, that's fine. We can go with 0.001. So if I look at my table, notice how quickly this is going down. So this is from this side, this is the left-sided limit. You can see as we get just a little bit closer to 0, these y values are just blowing up. And likewise over here, as we go closer and closer to 0 from the right. And then right at 0, of course, it's undefined. So what we have here is that the limit as x approaches 0 from the left of f of x, I don't want to say equals infinity, right? Because, well, I mean, you'll see that in your book. They'll say it equals infinity. I think that reinforces this idea that infinity is a number, and it's not. It's kind of a symbol that indicates that, well, and actually this is going to actually go toward negative infinity, right? As we approach from the left, this gets smaller and smaller and smaller. It decreases without bound. That's what, so we can kind of say this is tending toward, or it just gets smaller and smaller and smaller. There is no limit, right? I mean, it decreases without limit. And likewise, from the right, coming at it from the right, the function is going to just keep getting bigger, tend toward infinity. So here is an example of how a left-hand limit or right-hand limit doesn't exist, right? This does not exist. So this whole idea of the limit as x approaches 0 from the left equaling the limit as x approaches 0 from the right, this is what we need for the limit to exist. This can only happen if the left-hand limit and the right-hand limit both exist. If one of them or both of them don't exist, it's meaningless to talk about the limit, right? So, since the left tends to negative infinity, the right tends to positive infinity, then we would say that the limit as x approaches 0 of 1 over x does not exist. All right, now one thing that's important here, again, I don't want to contribute to this idea. I want to disabuse you of this notion right away that this is because f of 0 is undefined. Right? That has nothing to do with this. In fact, I will give you another example, very similar to this one, where f of 0 is defined and we have the exact same result. So I'm going to, we call this f, so let me define g of x to be 1 over x when x is not equal to 0. I'm going to call it 0 when x does equal 0. So it's going to look just like this function, except it's going to have a function value right there. All right? Now, in this case, notice, I have the exact same graph here. The only difference is I've put a function value right at 0, 0. Right? That's what this says. So what we have is that g of 0 equals 0. Right? But everything I've written here still applies, because what we're looking at is as you get closer and closer from the left, that's still true. As we get closer and closer to 0 from the right, this is still true. Therefore, that is still true. All right? So we would say that even though g of 0 equals 0, even though it is defined, we still have the limit as x approaches 0 of g of x does not exist. All right? All right, so that's the second way that a limit might fail to exist. And then there's one more that I want to discuss. An example of this is sine of 1 over x. All right, so if we take the limit as x goes to 0 of sine of 1 over x, what's happening? All right, so the graph here, we know that the range of sine is always between 1 and negative 1. And if you were to graph this, you would see a lot of this type of thing happening right here. And then as you got farther away from x equals 0, it would spread out a little bit. Well, it would keep going all the way up, right? And it would spread out a little bit here, right? So this is kind of, this is kind of a crude sketch of the graph. Let's look at what's happening in terms of, numerically, looking at the calculator here. So let's go back. I want to not see that one. I want to see this one. Let's graph it first. All right. Let's zoom in just once to see this a little bit better. All right. So here we see Yeah, doesn't look the same as what I have. If you graph it in GeoGebra, you would see it better. But I'm mainly interested in what's going on in terms of the table. So let's set our table to start at 0. 0.001 should also work for this. So if we look at our table values, so these are positive. So if we're going this way from 0.006 towards 0, this is like taking the limit from the right. And notice what's happening with our y values. I have negative 0.16, negative 0.87, negative 0.97, positive 0.32, negative 0.47, positive 0.83. They're just jumping around all over the place, right? Because what's happening here is, you know, when I put in 0.06, this is basically giving me, well, the inverse of it, right? 1 over that. But these 1 over x, we could actually put that in there too, right? Let's do that real quick just so we can kind of see what's going on. Whoops. So if we put this back in there, and now let's look at our table. So here is what's going on with our, what's in the inside part is 1 over x, right? So I'm taking sine of 166.7, sine of 200, sine of 250, sine of 333, sine of 500, sine of 1,000. So these just jump around, and you can see the same type of a thing. Whoops, let me get over here to x. The same type of thing is happening on the other side as we approach from the left, you know, so negative 0.005, negative 0.004, and so on. What's inside of here, my argument, sine of negative 200, sine of negative 250, sine of negative 333, and so on. So you're seeing some symmetry here because we're coming in at the same increment, and because sine is symmetric with respect to the y-axis. But you see this jumping around behavior here. All right. So what the jumping around is kind of the opposite of converging. Then that idea of kind of converging on a point is kind of an intuitive way of thinking about the limit. So what I have is, as I approach from the left, this thing just bounces around, and it bounces around more and more rapidly. All right. So the limit as x approaches 0 of sine of 1 over x, if we approach it from the left, it does not exist. Right there, that's enough. We don't have to, if we want to know whether or not this exists, the fact that one of the one-sided limits doesn't exist, we're done. I mean, just to look at this more carefully, obviously coming at it from the right, we have the same thing going on. All right. If you look at it in GeoGebra and really zoom in, it starts to look like a barcode. It's just bouncing, wildly all over the place. So we have this. We have the limit as x approaches 0 from the right. Sine 1 over x. That also does not exist. Together or separately, they imply that this right here does not exist. All right. So we've seen 3 ways that the limit might fail to exist. Just a reminder, so this was our first example, that the one-sided limits existed, but they weren't the same. We have this type of a thing going on. So that's one way. Another way was that the one-sided limits could tend to positive or negative infinity. The other thing I should point out here is one of these would have been enough. It's not because this one's going to negative infinity and this is going to positive infinity. All right, because I could change this to 1 over x squared, and then I would have something like this, and whether you're coming in it from the left or the right, they would both go to positive infinity. But this, basically, for the one-sided limit, that's a does not exist. All right, we might write that it tends to negative infinity or that it tends to positive infinity, but another way of saying that is that it does not exist. All right, so all you need is one of these to happen, and the limit of the function at that point doesn't exist. And the third one is the one I just discussed, this wild oscillating behavior where the left and the right hand limits, in this case neither of them, they don't settle on a particular value, they just bounce around all over the place.